Hi, this is Harlan Emil Gruber, and welcome to Portal to the New Earth. Today we're going to be going through the 3D sacred geometry that I utilize in my portal installations, and just a general explanation of the basic 3D geometries. But first, we're going to start off with an explanation of the golden ratio, as it's an intrinsic part of all of these geometries that I'll be showing. So the golden ratio is a way to divide any length so that the longer part divided by the shorter part is the same as the whole divided by the longer part, as you can see in this diagram. And so what that means is that 0.618 is to 1 as 1 is to 0.618. And it's actually an irrational number that goes on infinitely, but in the fourth decimal place is a 0, so 0.618 is very close to exactly the golden ratio. Another way of viewing the golden ratio is in this diagram of the golden rectangle, which is a rectangle that is made up of the golden ratio as the smaller to the longer sides of the rectangle. And then what you do is you divide the rectangle into a square, which leaves a smaller golden rectangle. And you can keep dividing the rectangle into smaller squares and smaller rectangles, and inscribing an arc into all of those squares creates what's known as a golden spiral. And this diagram here shows how both the golden ratio and golden spiral appear all throughout nature. And besides appearing throughout nature and in basic geometric forms, it appears in ancient temples and art because the ancients understood the importance of this. But even as you can see in the upper right, each digit of the finger is a golden ratio up to the next section of your fingers. Another way to understand the significance of the golden ratio is with the Fibonacci sequence, which was discovered in the Middle Ages by a scientist named Fibonacci. And it's interesting because the golden ratio is also called the Greek letter phi, and he has that in his name. Well, anyway, starting with just 0 and 1 and adding them together to create the next number in the sequence, at first it doesn't look like it's going anywhere. 0 and 1 is 1, 1 plus 1 is 2, 2 plus 1 is 3. But then it starts to diverge with 2 plus 3, 5, 5 plus 3, 8, and the higher you go up into the sequence, the closer each number gets to the golden ratio to the next number. And as you can see, just at 3 digits, 610 to 987 is exactly the golden ratio to 5 decimal places. And here is a chart that shows as you go up the Fibonacci sequence that it levels out and becomes exactly the golden ratio. And so now with this basic understanding of the significance of the golden ratio and how it relates to nature and numbers, we're going to dive right into the three-dimensional geometry. We're going to start off with the 5 platonic solids. As you can see on the left, each one separately, and on the right, them nested inside of each other. And then we have this animation showing all 5 of them. The first is the tetrahedron, 4 triangles. Then there's the octahedron, 8 equilateral triangles. The cube, or hexahedron, which is 6 squares. And a dodecahedron, 12 pentagons. And then the icosahedron, 20 triangles. And the reason why there's only 5 of these platonic shapes is that they satisfy both having the same number of faces around each vertex, and each face is an equal-sided polygon. And these are the only 5 shapes that fulfill both of those requirements. So now here's another way to see the significance of the relationship of all 5 platonic solids. Starting with the tetrahedron, each corner is truncated. When you get to the halfway point there, it is an octahedron. So then as you truncate each corner of the octahedron, we're going to stop halfway, which has 6 squares of a cube and the 8 triangles of an octahedron, which is called a cube octahedron. Then as you continue truncating each of the corners, it goes all the way to a cube. So you could see that if you cut the corners off of a cube, it would just go back to an octahedron. So instead, what we do is we cut the edges equally off of a cube. And this then creates the dodecahedron. And then from there, we cut off each corner of the dodecahedron, And again, this will stop halfway to show the shape that's halfway to an icosahedron called an icosahedron, which has both 20 triangles of the icosahedron and the 12 pentagons of a dodecahedron. And then we continue to cut off all of the corners until it becomes an icosahedron. So pretty interesting to see the relationship of all 5 of these shapes to each other. So now we're going to go into exploring the relationship between the cube and the octahedron, which, as we saw in the last animation, and as we see here, when you cut it off halfway, they become exactly the same shape, the cube octahedron. Well, this is a really significant shape. And here's a static diagram showing the same thing of truncating each of the corners, where the octahedron becomes a cube and a cube becomes an octahedron. Another interesting relationship of the cube and the octahedron is that they are duals of each other, which means that the vertex of each of them will sit directly in the center of the face of the other. As you can see in this diagram, with the cube touching the middle face of the octahedron and the octahedron touching the middle of each face of a cube. But there's another really interesting relationship that creates this cube octahedron, which is that if you start with a sphere of unit radius, you can pack 6 more around it in a plane. Then 3 more can pack below it, and 3 more above it. And when you connect the centers of all of these spheres together, not only does the outside shape make a cube octahedron, but you can see that it's made up of 8 tetrahedrons all coming together, touching in the center. And this is a shape that Buckminster Fuller discovered and called the vector equilibrium. And that's because each of the vectors starting from the center out to each corner is the same length as each of the vectors that surround going from corner to corner, which means energetically this shape is in perfect equilibrium. It would neither want to collapse on itself or explode outward, as vectors represent the amount of energy applied to the structure. And here is a static diagram showing those 8 tetrahedrons coming together, and also all of the closest packed spheres connected together to make the shape. Another relationship of the cube and the octahedron is that when embedded within each other, as you see here, and connecting all of their vertexes, it makes this other shape called a rhombic dodecahedron. And as you see across the top, the rhombic dodecahedron can be made from a cube by crossing the interior angles with diagonals, and then taking those pyramids and inverting them onto each face. And so this shape is actually the dual of the cube octahedron, and it contains both the cube and the octahedron in it. So now we're going to move on to a cube where we cross each of the diagonals on the faces. And then we'll actually remove the cube, and that leaves 2 tetrahedrons interpenetrating each other, or 8 tetrahedrons surrounding a central octahedron. So you can see that this shape then is kind of the converse of the cube octahedron, with the 8 tetrahedrons pointing out as opposed to 8 tetrahedrons pointing in. And here's a static diagram showing starting with a cube, crossing the faces, and leaving the central star tetrahedron, and how it's made up of 8 tetrahedron around a central octahedron. So here are these 2 shapes, the star tetrahedron and the vector equilibrium. So another really profound relationship of these 2 shapes was discovered by the physicist Nassim Haramein. And as you can see, on the left-hand side are the 8 black tetrahedrons coming together, pointing inward to create the cube octahedron, or vector equilibrium. And on the right-hand side, the 8 tetrahedrons coming together to make a star tetrahedron. And in the center, you see them both overlapping and interpenetrating each other to make this 64 tetrahedron grid. And so one of the interesting aspects of this 64 tetrahedron grid is that it's made up of 8 star tetrahedrons coming together to make this larger 64 tetrahedron grid. As you can see in this animation, and in this color diagram showing the 8 star tetrahedrons, each individually colored, coming together to make this shape. But another really interesting aspect of it that can be seen in this model that I actually created and painted is that you can see around the outside of this shape is both the orange and red star tetrahedron, but also a yellow cube octahedron or vector equilibrium. But in the very center is a light blue cube-octahedron. So you can see that this shape is actually concentrically nested cube-octahedrons. And it's also a fractal, which means that if you were to divide all of the struts in half, that central cube-octahedron would become the exact same shape as this outer full-size one. And if you were to double each of the struts, it would again create the same 64 tetrahedron grid, twice as big. So you can infinitely double or half each of these struts, and it makes the exact same 64 tetrahedron shape, infinitely inward and infinitely out, which is the definition of what a fractal is. And so what Nassim Haramein discovered with this shape, which he calls the structure of the vacuum, is this is how empty space, or the vacuum, which is what physics understands most of space to be, even inside of all atoms, it's mostly empty space. And they see that empty space actually has a nearly infinite amount of energy. So this is how all of the energy is balanced out to look like a vacuum. And there's so many corollaries to this shape, such as the I Ching, which is a Chinese divination, an ancient Chinese divination technique that is made by creating 64 hexagrams made of 6 lines. And through this divination, you're able to explain anything that happens anytime, anywhere in the universe. And 64 hexagrams is an exact correlation to the 64 tetrahedrons, which are made of 6 lines. Another interesting aspect I found in the name of this, the structure of the vacuum, is that there's a Tibetan prayer called the Heart Sutra, which starts off by saying form is emptiness, emptiness is form. And this can be thought of the form of the emptiness. So to really fully understand this shape is a way to understand the very fabric of the way the universe operates. And one last relationship is that when you have a 2D projection, which is what you can nearly see perfectly in this photograph, but you see in this graphic, that a 2D projection of the 64 tetrahedron structure of the vacuum, each of the crossings correlate exactly to the flower of life, which is, of course, one of the cornerstones of two-dimensional sacred geometry. So you can see this relationship between two-dimensional sacred geometry and three-dimensional sacred geometry. So from here, we're going to dive back into the platonic solids and look at the dodecahedron and the icosahedron. As we saw earlier, when you truncate the corners off of both of these shapes, it creates what's called an icosahedron, having both 20 triangles and 12 pentagons. And just like the relationship between the cube and the octahedron, these two shapes are duals of themselves, which means that the icosahedron, each vertex will touch the center of each of the faces of a dodecahedron, and conversely, the corners of the dodecahedron all will touch the center of the faces of an icosahedron. Another relationship between these two shapes is starting with a dodecahedron. If you stellate out each of the faces into a 5-sided pyramid and you connect the vertices of this stellated dodecahedron, it makes an icosahedron. So you see in this graphic animation and then in this static animation showing the stellated dodecahedron connecting the vertices into an icosahedron. And this brings us to the last of the 3D geometries which we'll be exploring. It's a shape that I learned about only in 2010 from a video by Drunvalo Melchizedek called Birth of a New Humanity. It's a rhombic triacontahedron, 30 rhombuses. When you cross the long diagonals of this shape, it creates the icosahedron. And as you see now, the short diagonals creates the dodecahedron. And a really profound relationship is that these diagonals are exactly golden ratio to each other. So you can see that this makes both a golden ratio icosahedron and dodecahedron. Another aspect, though, is by connecting where each of those cross will create the icosahedron that we saw in the previous animation. So all 3 of these shapes, or actually 4 of these shapes, the rhombic triacontahedron, icosahedron, dodecahedron, and the icosahedron are all completely related to each other. And the really most profound aspect is that through other research that I've done, this is what is being seen as the evolution of the Earth's vibrational energy body. So I've been using this geometry in several of my different portal installations. And here's the static image showing the relationship of all three of these geometries to the rhombic triacontahedron. So starting in 2012, I actually employed the rhombic dodecahedron in a portal I called the turquoise portal. And as you could see, when you go inside of it, each of the faces are crossed with the diagonals, so you could start to see the icosahedron and dodecahedron that's contained in this 30-faced rhombic triacontahedron. And it was colored turquoise to connect to the higher heart chakra, and the floor was colored a deep indigo to then connect to the third eye chakra. And I was invited for December 21st, 2012 to go to an event near the pyramids in Chichen Itza, and I created what I call the New Earth Grid Star, which is just the golden ratio icosahedron, dodecahedron out of this copper pipe. And here you can see it being used on the morning of December 21st, 2012 in a ceremony that was held just outside of the pyramids in Chichen Itza. Thank you so much for joining us today and learning about all of these 3D geometries. So I hope that you'll like and subscribe and share this video with other people. And if you're listening on the podcast, of course, you'll want to come back and be sure to watch the video so you can actually see all of these images. Thank you so much for joining me today.